Welcome to AI Paper Podcast. We're the place where we break down the latest research papers so you don't have to. Today, we're tackling something that's always a bit of a headache in AI. Getting amazing results, but getting them fast. It often feels like this constant battle, right? Quality versus speed. But what if a paper came along that really challenged that whole idea? Exactly. That's what we're diving into today. The paper is Seed Diffusion, a large-scale diffusion language model with high-speed inference, and it's a collaboration between ByteDance Seed, Tsinghua University's Institute for AI Industry Research, that's AR, and also the SIA Lab, which is a joint effort between Tsinghua AR and ByteDance Seed. Quite the lineup. A really strong team. Okay, so let's unpack this for you, especially for those of you maybe working as AI researchers or ML engineers. The basic problem they're hitting head on is something you probably face. Large language models, particularly with something complex like code generation. They often have this bottleneck. You get really high quality code, potentially, but it's slow, like token by token slow decoding. That latency can be, pretty painful in real world apps. It's like waiting for your code to compile one tiny instruction at a time.
Right. And this is where Seed Diffusion comes in with a really clever solution. They introduced something called Seed Diffusion Preview. It's a large language model, but it's built on this discrete state diffusion idea. The really cool part, the reason we're excited, is how it generates tokens. It does it non-sequentially. Think parallel generation. Instead of one line after another, imagine like multiple developers coding different parts all at once.
Okay, and the speed, because that's the hook here.
Get this, 2,146 tokens per second. That's the inference speed they hit on H20 GPUs.
Wow. 2,000 tokens a second.
Yeah, and you compare that to other models out there like Mercury Coder or Gemini Diffusion, it's significantly faster. But here's the kicker. They're getting that speed while keeping performance really competitive on all the standard code benchmarks.
So it's not just fast, it's actually good.
Exactly. It basically redraws the map for that speed-quality trade-off in code models. It challenges that old assumption you have to sacrifice quality for speed.
That really is a game changer, especially for anyone deploying AI in real-time systems or, working on things like interactive coding assistants.
Definitely.
So to really get why seed diffusion is such a big deal, maybe we should step back for a sec. Diffusion models themselves aren't brand new, right? We've seen them work wonders in images, video.
Absolutely. The core idea is pretty elegant, right? You learn to reverse a process that adds noise. You start with corrupted data, maybe total static, and step by step, you remove the noise until you get back the clean original thing. It's that coarse-to-fine generation that gets you those super detailed images.
Right, going from fuzzy to sharp. But language, code, that's different. It's discrete. Words, tokens. Not continuous pixels.
Precisely. And that's the core challenge. Standard diffusion works in continuous spaces. You can't just, smoothly add noise to the word import until it becomes deaf.
So how do people usually try to make diffusion work for text or code then?
Well, there have been sort of two main directions. One is you project your discrete tokens, your words or code elements into a continuous space, like turn them into embeddings. Then you do your standard diffusion in that continuous embedding space, and then project back to tokens at the end.
Okay, map it to a space where diffusion works, then map it back.
Yep. The other way, which is what Seed Diffusion really leans into, is to build the diffusion process directly on the discrete states. So instead of continuous noise, you define explicit rules, like transition matrices, for how the model can jump between token states. It's more about discrete denoising steps.
That sounds much more direct for discrete data like code.
It can be. But what's interesting is that even these advanced discrete diffusion models have historically run into a couple of major roadblocks for real-world use. First, there's this issue with token order modeling. Diffusion models can theoretically generate tokens in any order. That sounds flexible.
But language isn't like that. Code definitely isn't like that.
Exactly. Language, and especially code, is sequential. Trying to learn from every possible random permutation of tokens is just massively inefficient. It's like learning a sentence by randomly shuffling the words thousands of times. Often this actually makes them perform worse than models that respect that natural left-to-right sequence.
Yeah, you just get syntax errors constantly if you try to generate code completely randomly.
Totally. And the second big problem is inference inefficiency. Even though they can generate in parallel, that's the non-autoregressive promise, the actual process involves iterative denoising steps. Each step means running the input through the whole big model again. So even if you generate, say, 10 tokens at once, if you need 20 slow steps to refine them, well, your speed advantage kind of disappears.
Right. The parallel potential gets bogged down by the iterative refinement.
That's the crux of it.
Okay, so this is where Seed Diffusion Preview really makes its mark, tackling those two things head on. It's built for code, uses a standard transformer architecture underneath, but it's engineered specifically for speed and quality. And you mentioned it connects to the open source Seed coder.
Yeah, it builds on that lineage. So the core of their training approach is this two-stage curriculum, or TSC. Stage 1 is pretty much what you'd expect. A mask-based forward process. You take good code, randomly replace some tokens with a special M-mask token using a noise schedule, and train the model to predict the original tokens. Fill in the blanks.
Standard stuff for discrete diffusion, teaching it to repair corrupted code.
Right. But then, for the last 20% of training, they switch gears to stage 2, an edit-based forward process. Here, instead of just masking, they introduce explicit edit operations, actual deletions, insertions, substitutions guided by Levenshtein distance.
Levenshtein distance. That's about the minimum edits to change one string to another, right? So simulating real coding errors or changes.
Exactly. And this is super important. Why? Because just using masking can lead the model to become kind of overconfident. It might learn that if a token isn't masked, it must be correct, which means it gets bad at self-correction. If it only ever fixes masked tokens, it won't learn to review or change unmasked ones.
Ah, I see. It doesn't learn to refactor or fix subtle bugs if the token wasn't explicitly hidden.
Precisely. The edit-based part forces it to reevaluate everything, masked or unmasked. It learns to consider actual edits. This dramatically improves its calibration and enables that crucial self-correction ability during inference. It's like teaching it not just to fill gaps, but to actually review and improve the whole code snippet. It tackles a really tricky bias.
That's clever. Building in robustness. But what about the other problem? Learning from all those weird, unnatural generation orders, how do they fix that inefficiency?
Great question. That's where their constrained order diffusion training comes in. After the main two-stage training, they do something extra. They basically create a curated data set of good generation paths, what they call optimal generation trajectories.
Okay, optimal trajectories.
Yeah.
How do they figure out what's optimal? Are they guiding it towards more like left to right generation?
Sort of. They use the model they just trained to generate a bunch of possible ways to arrive at the final code sequence. Then they filter these candidate trajectories. They use a metric called the evidence lower bound, or ELBO, to pick the trajectories that are most probable and efficient, essentially, the cleanest, most likely ways the model could have generated that code.
So find the good paths, discard the noisy, inefficient ones.
Exactly. Then they fine-tune the model specifically on these high-quality synthesized trajectories. It's like giving the model extra lessons focusing only on the most effective ways to generate code, steering it away from learning those random, unhelpful orders.
Makes sense. Focus the learning.
Yeah.
But we still have those iterative steps, right? Even generating in parallel within a step, lots of steps mean latency. How did they speed that up?
Right, that's the final piece. On-policy diffusion learning. The goal here is to explicitly make the model generate good results in fewer denoising steps. They optimize the reverse process, the generation part, to minimize the length of the trajectory it needs. But crucially, they pair this with a model-based verifier. This verifier checks that the faster sampling process still converges to a correct, high-quality output. So it's pushing for speed, but with a quality check built in.
Fast and accurate, not just blindly cutting steps.
Exactly. They mention it's analogous to mode filtering in non-autoregressive text generation, basically, learning to find the best generation path quickly.
And they showed real results from this.
Oh, yeah. The paper actually tracks the speed-up ratio during this on-policy training phase. They achieved a massive plus 423% speed-up just from this step.
Wow, over 4x faster just by optimizing the generation path. That's huge for practical use.
It really is.
So, okay, we have this two-stage training for better correction, constrained order learning for efficiency, and on-policy learning for fewer steps. How does this all come together at inference time? How do you actually run this model fast?
Yeah, that's the practical side. They use what they call a block-level parallel diffusion sampling scheme. It's not fully parallel across the whole sequence, and it's not strictly token by token. It's semi-autoregressive or semi-AR. You generate code in blocks. The order between blocks is maintained. Block 2 comes after block 1. But within each block, all the tokens are generated in parallel using the diffusion process.
Okay, so you get some structure from the block order, but parallelism speeds up the generation within each chunk, a hybrid approach.
Exactly. It balances structure and speed. And they use KV caching for the previous blocks.
Standard optimization, remembering past calculations so you don't redo work for the next block.
Right, saves a lot of computation. And importantly, that robustness they built in earlier from the constrained order training helps ensure that generating block by block doesn't significantly hurt the overall quality. They also stress that it's not just algorithms, it's holistic system optimization. They clearly leverage their internal infrastructure, building specialized optimizations specifically for this diffusion sampling.
Engineering matters too.
Absolutely. They even show analysis, like in Figure 2b of the paper, looking at the optimal block size to minimize computation time. Finding that sweet spot, it shows real engineering depth.
Incredible. Okay, so the engineering is there, the algorithms are clever. Let's talk results. The benchmarks. How do they prove this thing actually works well on real code?
They went pretty broad and deep with the benchmarks. For just fundamental coding ability, you've got the standards, Human Evil and MBPP.
Okay, basic Python coding tasks.
Then for more real-world complexity, multi-tool use, reasoning, they use Big Code Bench. That one has over 1,000 tasks across different domains. Really tests robustness.
More challenging stuff.
Then there's Live Code Bench, which focuses on competitive programming problems. What's cool there is it's continuously updated and everything's time-stamped, so you avoid evaluating on data the model might have accidentally seen during training.
Good for checking against contamination. What about other languages?
Yep, MBXP for multilingual evaluation covers over 10 languages.
And editing. Because often we're modifying code, not writing from scratch.
Crucial point, they used Aider and Knide Edit. Aider looks at applying changes based on specific formatting, like applying patches. Knide Edit tests understanding more descriptive or even ambiguous instructions for modification. Really pushes the editing capability.
Wow, that's a seriously comprehensive evaluation suite. They covered a lot of ground. So the moment of truth, what were the performance highlights? Give us the bottom line.
Okay, headline number again. 2,146 tokens per second on H20 GPUs. Blazing fast. But the critical thing for you, as someone potentially using this, is that it achieves the speed while maintaining competitive performance. It's right up there with advanced autoregressive models on all those tough benchmarks we just listed.
So, speed without the quality sacrifice.
Precisely. It establishes a new state-of-the-art on the speed-quality Pareto frontier for code models. They push the boundary, and specifically, they noted a notable boost on editing tasks. That's a big deal for practical developer workflows.
That's really impressive. It feels like a genuinely significant step forward.
It really does.
Okay, so wrapping up this paper podcast on Seed Diffusion, the key takeaway seems clear. This is a major advance for diffusion models working with discrete data like code. They've managed to balance that tricky trade-off between speed and quality in a really elegant way.
Yeah, and if you think bigger picture, it's also super interesting as a research direction because it challenges that default assumption we often make in AI that generation has to be sequential left to right, the way humans typically read or write. The authors talk about moving away from this pervasive human-centric assumption. Maybe there are fundamentally different, more efficient ways for AI to process and generate information.
That's a fascinating point. It really makes you think. And maybe that's the provocative thought for you listening. If rethinking generation order gives us this kind of speed boost for code, what other AI tasks are currently stuck behind similar human-centric assumptions? Where else might non-autoregressive approaches or totally novel generation strategies unlock performance breakthroughs we haven't even imagined yet? Could it impact your own research or engineering work? Something to mull over. If you want to dig deeper yourself, definitely check out their project page, seed.bytedance.com/Seed Diffusion. And there's a demo too at studio.seed.ax Seed Diffusion. Definitely worth exploring. Thanks for tuning into AI Paper Podcasts.